back. You hit that, the screen goes off, and like.
Good morning. The guidance we got was to tell a few stories. Today's stories will be high-energy lasers, specialty lasers, and other light sources, micro-discharge arrays. These are stories that I like. I hope you will too. Key scientific areas, many, because I've been in lasers and applications of lasers my entire long career. It involves many things. It involves materials, nonlinear phenomena. Lasers are inherently nonlinear. Plasma phenomena, discharge lasers, et cetera, et cetera. Again, many Air Force applications, potential applications, directed energy weapons, advanced countermeasures. We already have contributed to the Air Force large aircraft in what you might call simple countermeasures, that is countermeasures to simple missiles. They work all the time. Force health and readiness, some spectroscopy, for example. Let me not read them all. Additive manufacturing, we were involved, this program, in laser additive manufacturing well before that became a buzzword. Novel chemistries for fuels, lubricants, et cetera, and I'll show you some of that later. Top-level description of portfolio, and again, things I'll talk about. Ceramic laser materials, fiber optic materials, related fiber optic beam combining, made in semiconductor lasers, molecular dynamics, light emission from molecular discharges, micro discharges, and special chemistries that also go on micro discharges because of their special properties. Investment strategy, strategy is used in a lot of different ways. This is one way. We have, I think, the only at least sizable basic material studies for high-energy lasers. Many people do high-energy lasers with existing materials, modifications of existing materials. We have major program in new materials. We just got a BRI for fiscal 15 in that. I can do that because I work with a genuine materials expert. He's in the audience, Ali Sayer. World-leading theory, materials, novel growth, and characterization of mid-infrared semiconductor lasers. That's an in-house program at RD with Dr. Ron Caspi. He's in the audience also. I'm very lucky I have experts in the audience who can answer all your questions. Pioneering and world-leading studies in micro-discharges. That started with a program with Gary Eden and expands. We're looking at their light emission characteristics and their possibilities for special chemistries. With success, I'll talk to you about in ozone generation very efficiently. That's, again, with John Lukinsland, who knows much more about plasmas than I do. So getting into the ceramic laser gain material, ceramics have a lot of advantages over other solids for solid-state lasers. Ceramic materials can be fabricated with arbitrary shapes and size. You can make a ceramic as large as the oven you have. Ceramics are well suited to produce composite gain material. Spatially varying doping and index profiles give you flexibility in design and get you more efficiency. Significantly higher doping concentrations are possible. Some materials, for example, sesquioxides, are very interesting interesting laser materials are relatively easy to make in ceramic form than they are in single crystals because they require very high temperatures. Relatively easy because actually there was a program by JTO. They didn't have terribly much success. There's some ongoing work at NRL now, which is having more success. The FY15 BRI that Ellie Sayer and I have, these are some of the slides that we used in presenting to get that BRI. The background, transparent ceramic materials are great. They've led to breakthroughs in high average power. A couple of years ago, Northrop Grumman had a milestone. They showed 100 kilowatts out of a ceramic solid-state laser funded by JTO. Everything that's done good stuff is purchased from the Konishima Chemical Corporation in Japan. This is not a big line for them, and they're quite secretive about process. The ceramics have limited power handling capability. The Northrop Grumman system has 2 legs with multiple amplifiers. It's not ready for prime time yet. And most importantly, there's a limited knowledge or control of defects, dopants, impurities, index of refraction, thermal conductivity, etc. In other words, many of the advantages I showed you on the previous slide have yet to be realized. We have had a small program in ceramic materials ongoing, some accomplishments to date, precise measurement of very small absorption and how that varies with processing conditions, and identification of the absorbing impurities, mostly silicon. That work is done at Stanford. It's possible because a few years ago, for general purposes, we bought them a photothermal measuring device that can measure very, very small absorptions. Done initial experiments using LIBS to study what goes on while you're processing. LIBS is laser-induced breakdown spectroscopy. I had production, as Dr. Roach told you, of very small powders to make a very interesting material, SFAP, strontium fluorapatite. For those of you who don't know, fluorapatites is what your teeth and your bones are made out of. They're an open material, they're very good for lasers, not so good for your teeth. And we've had production of very low loss slugs of that material, as I'll show you in the next slide. This is work by Dr. Yokan Wu at Alfred University. Alfred has a major ceramic center that was supported by the state of New York. He's gotten high quality laser quality material. It's outstanding because it has properties you might like for a laser. He has new process development. It's a prototype for other non-isotropic ceramic materials. If you have an isotropic material, all you have to do is squish the grains together, make small boundary condition, small grain boundaries, and you get low scattering. If you have a non-isotropic material, that's not good enough because you will, if they're not aligned, you will still have big index variations and big scattering. So you have to either get the grains much smaller than a wavelength to get the scattering low, or you have to align the grains. If you can align the grains, then you have potential to make frequency converting nonlinear materials using quasi-phase matching by varying the alignment every coherence length. Low loss is essential if you're going to make high energy lasers. This is just to illustrate how that's come about. You see on the left axis how the loss has gone down over years, and on the right how the power has gone up in years. The highest point it's too much trouble to use the pointer, but the highest point is the Northrop Grumman 100 kilowatt. Moving on to fiber lasers, things we're considering are beam combining both coherent and incoherent, tandem high power lasers where one fiber laser pumps another, advantages of that. High power pulse lasers at RD, photonic bandgap lasers. We and everybody else are studying those, but we're studying some special properties and some special configurations. Mode-locked infrared fiber lasers had some very good results, particularly on some STTRs we've had. And applications of those, particularly in writing both index guides and actually etching in materials, particularly glasses. For example, for making flow MEMS. The BRI topic we got in fiscal 14, I got with John Gunklewski. We'll look at ways to get high power from single fiber lasers greater than 100 kilowatts. Right now, people get 10 kilowatts. You can buy 10 kilowatts commercially, single transverse modes, but that's probably where it's going to stop. You're at some physical limits there. The game is to make extra large areas so you don't have too much intensity, but you still can get numbers like 100 kilowatts. That's going to require research into new materials and new configurations. If you try to coherently beam combine so that you take a lot of these lasers and try to make them look like one big laser, you run into trouble, you run into instabilities if you get much beyond, say, 5. With research that we funded, maybe you can get to 10. So if you can start with 100 kilowatts and combine 5 or 10, you're talking serious power. We hope that this BRI, we expect that this BRI will also provide a university source of specialty fibers to do collaborative research, particularly at RD, but also at other universities who have good ideas and can get fibers from this program. We've already selected who we hope to fund with this program, but I can't tell you because the funding hasn't been released yet. Again, from our FY15 BRI presentation, glass fibers are very promising for high average and peak powers, but they have serious limitations. Photo darkening, nonlinear phenomena, mode control if you try to get very high power and go to large areas. Beam combining can lead to instabilities. These are well known. They were predicted actually quite a while ago, ignored and then observed and are limiting. High average power lasers are based entirely on glasses studied and evolved for telecommunications with only small variations. Other glasses, which would have important advantages, need studies. You know they would have important advantages, but you also need to know how to produce them at very low loss. That's not possible yet. The Russians do some very good work, for example, on barium fluoride glasses. Some useful work is going on in other countries, Germany and, as I just said, Russia. So the objective of that BRI, which is now going to be funded, at least for now, new fundamental studies of glasses and transparent ceramic materials, focus on understanding the materials properties, bring new theoretical and experimental techniques not usually associated with the materials community to understand the processing of those materials and their problems. For example, Ali knows the materials very well. There are spectroscopic techniques that I've known all my life. We bring to bear on that. focused on high-energy laser materials, but with transparent materials in general, for example, domes. And as well to broader non-optical applications as well. Moving on, let's talk about the semiconductor laser work that goes on at RDL. I will try to describe this work. I hope Ron Caspi, wherever he is, won't grimace at my explanations. Two things to talk about. One is high-power quantum cascade lasers. Another is quinary alloy room temperature lasers that he has just started working on and has had some very good success. The quantum cascade lasers become very popular. They can produce compact laser sources that emit mid-infrared and longer wavelengths, terahertz even, with a promise of high brightness at room temperature. Broad area devices that might give you high power suffer from all filamentations and other instabilities. Narrow ridge devices then are required to maintain single transverse mode. So to get high power, you have to make very long cavity devices, very long narrow cavity devices. The narrow and long cavities suffer from low yield, high cost, facet damage, because you're concentrated across small areas, high beam divergence, etc. And Ron's group has recently developed a novel technique to produce laterally coherent beams from broad areas and to solve those problems above. Pictorial, what I just said, if you have a narrow ridge, you can get something that looks like a single mode. If you have a very broad area, typically you will get beam breakup, instabilities, filamentation, and so forth. This, on the other hand, describes the achievements at RD recently, where they have got single transverse mode from a broad area. One of the keys is to just start with very good high-quality material. The other is the realization that under some conditions, you will get a high-order transverse mode, but a single high-order transverse mode, and it's very stable. Similar things have been noticed in fibers. You can then, by the way, do things to take that very high order transverse mode and get very high focusability out of it. His quinary laser work is just starting. It comes about because of their expertise in materials and fabrication. And it's producing relatively high powers, competitive with anything else at this point in the 3 to 3.5 micron band. That gives you lots of applications for chemical remote sensing, biological markers, for example, breath sensing, because mostly at the 3.4 micron region, you overlap the CH stretch of many organic molecules. You see on the graph at different temperatures, this is preliminary work, but if I can read this, 4 microns still exceeds anything that's ever been done before at room temperature. And it's got a long way to go. In general, I want to show you that the program we have at RDL in semiconductors is what a basic research program can be. It's completely integrated with 6.2 programs and much more advanced programs that transition. Some years ago, we were funding the optically pumped semiconductor lasers and the development of those. Those have now moved on. They're being packaged by Lockheed Martin's Acculite division. They're put into systems which are being studied to spoof heat-seeking missiles. Moving on, talking about micro-discharge arrays. We're doing research. These are, micro-discharges are discharges that are very small in dimension, of course, at least one dimension. Small, we mean 100 microns or less. These the microdischarge has very interesting properties. I do this work with John Lugansland. When I say things like their Debye lengths are larger than the device, for example, or their electron distributions are non-Maxwellian. I know what that means if I think of it. John intuitively knows those things. On the other hand, for me, what's down in the bottom right, PD scaling, is very important. PD scaling means the pressure you can get in a stable discharge varies as you make the diameter smaller. PD stays roughly constant for how you can make a stable discharge. I've had experience with this, for example, early on in helium neon lasers, later in CO2 lasers. CO2 lasers, as a background, are very interesting because as you scale the diameter down and you can increase the pressure, you can keep the power constant. So the power you get out of a CO2 laser is totally independent of the diameter of it. We're looking at the physics and chemistry of those, John and I both. Electronic elements, plasma transistors. I'll show you what that means in the next slide. Novel nano solid materials. John has programs in that. And I have programs to make long, narrow lasers, very simple laser arrays in the UV, the VUV, and the extreme ultraviolet. Had some technology transfer in this, helped along by some STTRs we have funded. Two spin-off companies from Gary Eden's work at the University of Illinois, one in specialized lighting, including ultraviolet lighting, one in ozone production and other specialized chemistries. They've been quite successful, as I'll show you in a minute. Here's what the plasma transistor looks like. Uses a semiconductor emitter and base and a plasma collector. The fact that these can be done is not new. I mean, Shockley wrote about this in his classic 1947 book. But it's getting attention, particularly from the microdischarges, and with some very interesting properties. For example, if you want light, you can use the amplification from the plasma. You can use the amplification in the transistor to do that at very low voltage. You can also, obviously, since you don't damage the plasma, do very high power stuff. Example of the UV and VUV lasers, because you can run these at very, very high pressures. PD scaling works all the way down to 100 and probably 10 microns. You can get very high pressures, and so you can get species that you normally don't get in discharges, namely eximers, for example. So you can get very bright UV. Gain has been seen in these, so far not lasing. There's a very interesting sort of thing that Gary has done, maybe not so closely related, but I liked it, so I put it in. This is a plastic microsphere. You buy these things. You can buy them actually with this protein biotin attached to them. They're used in various biological things. He puts this on a plasmonic array. This is etched silicon that has points, and you deposit gold on it. Put another protein and then a dye. All that is just to get the dye on the thing. Now you can pump this optical excitation with milliwatts. You can pump it with a helium neon laser, and you can get it to laze. You go in whispering gallery modes of this sphere. The plastic is not so great as far as an optical material, so you only get finesse like 300 or so, but still enough to get lots of round trips. The evanescent wave gets amplified by the dye, well, first you get Raman scattering about 100 wave numbers in the plastic. That gets amplified by the dye. You get a very pure Raman line, single Raman line. You normally don't get, normally you get lots of Raman lines when you do this kind of thing. What's it good for? I don't know. We'll see. The microplasmas have been made in large arrays, many thousands, millions of micro-discharges. They make wonderful lamps. They're being sold to Hollywood because they give you very natural lighting. They could also be used, for example, for special forces because you can roll them up. You can individually address things, so you can make displays out of them. Large area ultraviolet lamps for water disinfection and cooling, and polymer curing. Also, by flowing air through them, you can very efficiently, more efficiently than any other process, both in terms of grams per hour and in terms of amount of ozone per watt you put in. You can make ozone. Right now, the company is selling them as fast as they can produce them to institutional laundries. The EPA just decreed that you must use cold water, must use hotter water or else disinfect more with ozone. So that's a basis for a lot of the sales. The ozone generators are small. They could be used, for example, by special forces to carry around to purify water. UV is also used to disinfect water, usually mercury lamps. There's a major company in Canada that sells lots of product for that, all based on mercury lamps. Company is called Trojan Industries. Usually when I say that, people think of something else. Disinfection of drinking water, as I said, food preservation, many applications for efficient ozone production. Ozone is used for lots of things now. You can buy an ozone generator, for example, for water pick, but it's not nearly as good as this. Example of the microplasma lamps, 6 by 6 inches, each one about 100 microns, each discharge about 100 microns. There's a process for making these very inexpensively. These are now up to 12 by 12 panels, standard for Hollywood lighting. Luminance efficacy has been 25 lumens per watt. It's increased to about 50. That's about half of what an LED does. LEDs do not give you very natural lighting, and that's why they're not used in some applications where you have to filter them like crazy if you're doing video. CRI is of 80. CRI is a measure, again, of how good is the lighting, how natural is the lighting. These lighting panels have won awards at both the 2012 shows for the National Association of Broadcasters. Example of a UV lamp that's not as far along that could be used for disinfection. The mercury lamps that are used are effective. They're not either as effective as you would like or as inexpensive as you would like. You'd like to go to shorter wavelengths to get more bacteria. Again, use UV and ozone together. Problem is, of course, there's a lot of infrastructure based around mercury lamps. The other problem mercury lamps have, of course, is that they do use mercury. Example of ozone production from a company now called EP Purification, based on this thing on the right, the module I don't know if you can see the little bit of the lines that go across those circles. Those are the micro discharges. Air comes in one side, flows out the other side, and the ozone is produced. You can stack these to make as big a unit as you like. Okay, I'm going to switch gears again. Each year I've tried to tell you about some really major technology transition this program has had over the years. 2 years ago, Rick Parra filled in for me and told you about optical coherence tomography. We funded that because it looked interesting. We had a smart young guy at the time. This was about 28 years ago. It turned out the biggest, but hardly the onlyest application is in medicine. 2012, there were about 16 million eye procedures performed with OCT. It's become the standard of care in eyes. It's becoming the standard of care in coronary artery disease for seeing what kind of plaques you have, and for placing stents. Many stents, unfortunately, these days are misplaced, do more harm than good. Last year I told you about our work in contributing to infrared optical parametric oscillators that go on every large Air Force aircraft and do spoof almost perfectly early heat-seeking missiles like the Stingers that the U.S. once sent to Afghanistan. This year, I want to tell you about our contributions to vacuum ultraviolet excimer laser lithography. This is a slide I showed many years ago in a spring review. I think it may have been called a fall review at the time. And early work by Jane at IBM had suggested the idea of excimer lasers for lithography. It was, at that time, a long way off. We were funding Dan Ehrlich and Mordecai Rothschild, his postdoc at MIT Lincoln at the time. Dan had a very good idea. He said excimer lasers intrinsically put out high peak power pulses. So why not use some non-reciprocal resist, something that would respond to the peak power, but wouldn't respond at all if you had the same average power. And he chose a diamond-like film to put down and blew away at it. At the time, there were no good transmitting optics at 193 nanometers, so he used a reflecting optic that was good enough, a so-called Schwarzschild reflector optic. And he produced this pattern of 130 nanometer lines. This got people excited enough that DARPA dumped $30 million at the time into could this become a lithography? It was far from clear. But step after step, resists were developed, optics were developed. Much of the program was run by Morty Rothschild. Many outside players, though, kept going. Industry put in money. Well, the bottom line of that story is subsequently and today, all today's microchips are made with excimer laser lithography, 193 nanometer argon fluoride lasers. Today's chips, I looked it up, an Intel i7 that you buy has lines that are about 22 nanometers, way less than the 193 nanometer. They do a lot of tricks to get there. They do immersion, which means they dunk the whole thing in water. They do large angle stuff. They do phase masks. They may be getting as good as they can get at that. If so, the next lithography may be XUV lithography. If that happens, I will be up here sometime telling you about our contributions to that. Nobel Prize winners, we make a big deal out of Nobel Prize winners. As Dr. Mattson told you yesterday, we funded Steve Chu early on to do cold atoms in the early 90s. 10 years before that, we funded Dave Wineland to do cold ions because I was interested in clocks. We have funded Art Shallow, got a Nobel Prize, John Hall, who got a Nobel Prize. More interesting future ones. Thomson Reuters does some kind of algorithm where they pretend they will predict future Nobel Prize winners. They have predicted Steve Harris and Lena Howe will win one of these days. I make less formal predictions. I predict Jim Fujimoto, who invented optical coherence tomography, will win one in medicine one of these days. Dr. Kirchick in her briefing will tell you a lot more about Steve Harris. And that's it. Further questions?